Great. Yeah, thanks for having me. And maybe for setting the stage for the remainder of the talk, let me start to introduce a very classical geometric problem. So we are looking at embeddings of the sphere, of the two sphere, into 3 space. And obviously there are many such embeddings. And among all these choices, there's certainly one which we prefer because of its symmetry. So the standard embedding is the round sphere. And it's a natural question to ask, what are the properties which distinguish this embedding among all the others? And one idea would be to look at the Riemannian metrics. So every such embedding induces a Riemannian metric on the 2-sphere just by restricting the Euclidean metric to our submanifold. And now we can rephrase and ask, what are the special properties of the metric of the round sphere, which characterizes the metric of the round sphere among all the other metrics which we can get in this way. And one characteristic property comes from the local invariant of the curvature. So as it turns out, the metric of the round sphere is uniquely given by the property that it has constant constant Gaussian curvature. So we have this worked better before. Let me increase the size here. So we have constant curvature, and alternatively, we can look at a global invariant of the metric, namely the volume. And as it turns out, among all the metrics, the metric of the round sphere minimizes the surface volume, or maybe surface area, but I'm going to call it volume anyway. So we get a minimal surface volume here. And in the way I've written it, it doesn't really make sense, because obviously I can always shrink the size of my embedding. So I'm shrinking the size of the radius of my sphere and make the surface volume arbitrarily small. So really, to make sense to the problem, or to make sense to the statement that we have minimal surface volume, I have to normalize the notion of volume. And the idea is to normalize it by the enclosed volume of the embedding. So in other words, I get only a minimal surface volume if I fix the enclosed volume of the embedding. Okay, and so what we observe here is we have 2 very different properties which both characterize uniquely the metric of the round sphere in our setting. So a posteriori, both characterizations give us the same canonical choice of a metric here. So let me say this is somehow equivalent, both characterizations. And yeah, so this is what we are going to take away from this board. And now we move on to, from geometry, if you wish, to algebra. So we now have a different problem. And so we fix, let's say, a ring. And to be more precise, we are going to fix a graded ring, a positively graded ring. So graded pieces like this. And we really want the ring to come from a geometric situation. So actually, we are going to look at a finitely generated C algebra here. And what else? We want, let's say, this C algebra to be Gorenstein. And maybe we want to have an isolated singularity. And last property, we want that the component of degree 0 consists only of the constants. And if you wish, you can, one more property, we want it to be log terminal. Okay, so and if you wish, you can think of the cone over a Fano manifold. And so I fixed the ring, but actually I fixed a little bit more. I also fixed a grading here. And such a choice of a grading is not necessarily unique. So there might be different possible choices. And to emphasize that we made a choice here, let me give this Z grading a name. So we have a Z grading. And we give it a name. I'm going to call it Psi. Okay, so and now we are in a similar situation. If there are different possibilities to choose a Z grading, then maybe we want to have a canonical choice, or we want to make a canonical choice among all these possibilities. And we take a similar approach as on the last board. So the second approach here, what did we do to make a choice of a canonical metric? We fixed an invariant for our metrics, and we tried to look for the metric minimizing this invariant. And we are taking the same approach here. We want to introduce an invariant for a Z grading, and we are trying to minimize a certain invariant for this Z grading. And this invariant is again called a volume. So a volume for our choice of a Z grading here. Okay. And how to define the volume here? We start, or we do it in two steps. We start with defining an ideal, which I denote by mk. And how is it defined? It's just this direct sum of all the graded components RL, where L is strictly larger than this fixed number k here. Okay, now we are interested in the quotient by this ideal. And I mean, first of all, this is a module over our ring, but because our ring is a C algebra, it's also a vector space. And we are interested in the vector space dimension of this quotient. And if you look at the definition of the ideal, then you see as we increase k, the ideal becomes smaller and smaller, and therefore the dimension of the quotient gets larger and larger, and actually it tends to infinity. So what we are really interested in is the asymptotic growth of these dimensions. And in fact, the dimensions grow like a polynomial of degree d in k. And I want to see how the dimensions increase compared to k to the d. So I'm looking for the leading coefficient of this polynomial, where d is just the Krull dimension of our ring. Okay, And yeah, so I'm interested in the asymptotic behavior. So this means I'm looking for the limit as k tends to infinity here. Okay, so this is my definition of a volume for a Z grading. Are there any questions at this point? So I'm assuming not. So the idea now is that we are trying to find a Z grading psi which minimizes this invariant. And so we want to turn our problem of finding a canonical choice of a Z grading for our ring into a minimization problem. And in order to solve such a minimization problem, it would be good to have some understanding of the space where these gradings live in. And this is what I want to talk about next. So we want to put our gradings into some space and then run a minimization problem on this space of gradings if you want. For this, let me change my situation a little bit, or adapt it, better to say. So I'm still having my ring R, and it's still going to be a graded ring, but now it's graded even over a larger lattice. Let me call this lattice M. So it's just some Z to the M. And all the other properties of the ring R are preserved. So I want it to be Gorenstein and have an isolated singularity and so on. And now the choice of my Z grading gets replaced by choosing psi in a vector space called NR, and this is just the vector space which corresponds to the dual lattice of M. So the M was the lattice where my grading comes from. So I'm looking for the real vector space associated to the dual lattice. And if you recall from the last board, I didn't look for arbitrary Z gradings, but only those which I called positive. And so I will have a positivity condition here as well. So what does positive mean? In this setting, positive here just means that I want the pairing of psi with the weight to be indeed positive whenever this is at least possible, so U is not 0, and the corresponding graded component is non-trivial. Okay, so now I'm looking for nice choices of this psi. And I have to adapt my definition of a volume to this new, slightly different setting of choosing psi as a vector in this vector space. But so how do I define the volume of such a psi here? I'm first again defining my ideal mk, and this looks very similar. So we take the sum over all RU, but this time such that the pairing of psi with U is strictly larger than k. And then I just copy my old definition. So I can literally do this. So I indeed copy the definition we had before, just we had to adapt the definition of our ideal MK to this new situation. Okay, so what does this have to do with our original problem? I mean, it's probably already clear, but let's make it explicit. So the remark here is that once I'm choosing my element xi, not just to be an element of the vector space NR, but actually live in the dual lattice of M, so it's a lattice element, then this gives rise indeed to a Z grading, a positive Z grading as we considered it before, namely I'm setting RL to be just the direct sum of all the graded components, such that the pairing of U, so the weight of the component, and our choice xi is equal to L. And this gives now just a Z grading, the object we are actually looking for. Okay, so we see our Z gradings being embedded as lattice elements of a vector space. Okay, so now one more remark concerning the volume. What happens if we are going to rescale such a vector? So let's say I take lambda times some xi. What happens to the volume under such a rescaling? And if you look at the definition, it's not too hard to see that the volume gets rescaled by a factor which looks like 1 over lambda to the d, where d is again the Krull dimension of the ring. So in particular, what we see is if we are trying to minimize or find a xi which minimizes the volume, then we are running in the same problem as for the embeddings of the sphere. Just by rescaling our vector xi, I can make the volume arbitrarily small. So again, we have to normalize our notion of a volume here. And so this is the next thing I'm going to talk about. How does the normalization work here? Recall for the embeddings of the sphere, the idea was just to fix another invariant, namely the volume of the enclosed volume of the embedding, and then look only for the metric which gives us a minimal volume with this additional condition. And we are doing a similar thing here. So if we fix another invariant of our vector xi, or of our Z grading. And what is this additional invariant? It's called the log discrepancy of xi. So, and let me just define it in an algebraic way. And so it's just the pairing of xi with a certain vector or a certain weight, which I call v here. So a certain element of our lattice M. And I'm going to call it the canonical weight. So recall that we assumed that our ring is M graded. So this means the canonical module of that ring will also be M graded. Now we also assume that we are in a situation of a Gorenstein ring. So this means our canonical module is generated by one element. And so this canonical weight now just stands for the weight of this generator. And if actually xi is a lattice element, this means xi gives rise to a Z grading, or alternatively, you could say it gives rise to a C star action on the spectrum of our ring. Then you can connect this to the usual definition of the log discrepancy. of a divisor, namely we are just looking for the C star invariant, unique C star invariant divisor over our singularity, which consists entirely of fixed points. So you could put it this way. Okay, so we introduced a new invariant for our ring, for our grading or for our choice psi. And now what is our strategy to find a canonical choice for psi? So strategy. So we want to find a positive psi in NR fulfilling the following properties. So first of all, we fix the log discrepancy of this psi. So what I just said, similarly, as we fixed the enclosed volume of our embedding and then run a minimization for the surface volume, we are now fixing the log discrepancy of psi and trying to minimize the volume. So this means we want A of psi to be 1 and want to choose psi such that the volume of psi is indeed minimal. Okay, so this is our strategy, and maybe we want to see this, how this strategy works in an example. Okay, and now I'm going to move to the toric case. So our setting is now as follows. So we fix a polyhedral, rational polyhedral cone in MR. So rational polyhedral, pointed, and so on. And we look at the ring, the usual toric ring corresponding to this cone in the M lattice. So we take the sum of all U inside this cone, intersect with the lattice, and then we take the corresponding semi-group algebra. Okay, and now recall we want to fix a choice of a vector in NR, and we want this to be positive. And if you look back to the definition, what did it mean to be positive? It just means it pairs positively with all the weights occurring in my algebra. So in other words, psi comes from the interior of the dual cone of tau. Okay, but again, we have many possible choices to choose our psi inside this dual cone, and our idea was to look for the choice which minimizes our volume. And in order to find such a psi, we need to express the volume in our combinatorial data here. So I want to calculate the volume of psi. And in order to do this, I have to introduce a certain truncated cone, tau of psi. And how do I truncate my cone? So I take tau and I intersect it with a half space, namely the half space where psi takes values less or equal to 1. Okay, so to give an example, we can take reflexive polytope, this one here, and we embed this reflexive polytope one dimension higher on a hyperplane in height 1, and then we take the cone over this polytope. So the usual construction. And let's say, so this is our tor here, and we fix certain choice of xi. Let's say we just fix xi to be 0, 0, 1. Okay, so now the hyperplane where xi takes value equal to 1 is exactly the hyperplane where we embedded our polytope. So this means if we truncate our cone and take only the part which lies below this hyperplane, we get exactly this picture here. This is our tor of xi in this setting. And now it's an observation that the volume of xi is just the volume of this truncated cone. It's actually not too hard to see this. Okay, so now we recall that our choice of xi was not arbitrary. So we had the restriction, we had a restriction on xi, namely that what we call the log discrepancy has to be 1, our normalization. What was the log discrepancy? It was just the pairing of xi with a certain vector, which I called the canonical weight of our ring. What is this canonical weight? Since we started with a reflexive polytope, the origin was the only interior lattice point, and then we embedded the polytope in height 1 in a vector space, and now the canonical weight is exactly what this interior lattice point inside our polytope here. So since we embedded this in height 1, the origin now is lifted to 0, 0, 1. Okay, so in this particular setting, this is our canonical weight here. Okay, let me now rephrase this condition, this normalizing condition, a little bit. We could rephrase it by saying that the canonical weight has to be an element of the hyperplane in M where xi takes values equal to 1. This is now our normalizing condition for xi. Okay, so if you're now trying to choose a xi which minimizes our volume, what does it mean in our picture? Now, yeah, so changing psi means we are going to change the hyperplane which we use to truncate our cone. But we don't change this arbitrarily, but we change it in a way that always this lattice point V is contained in the hyperplane. So we are somehow just tilting the hyperplane we see at the moment in every possible direction, right? But we are going to be careful that this lattice point, this yellow lattice point, is always contained in the hyperplane. So we get many, many different truncated cones in this way, but we are looking for the choice of the hyperplane which minimizes the volume of the truncated cone here. And this is our canonical choice of a hyperplane, or equivalently a canonical choice of a psi in the dual space. Okay. Are there questions? No. Okay. Yeah, let's maybe have a closer look at this example and to really see what is the result we are going to get here. What is our canonical choice, psi, in this particular example? Okay, if we want to calculate this, we can use a symmetry here, which helps us in our calculation. Indeed, it's easy to see that already the polytope we started with is invariant under this reflection, right? So let me call this reflection the involution sigma. And what does it do? It just flips the first and second coordinate here, or you could say it's induced by swapping the first and the second canonical vector in my vector space. And since everything is preserved by this involution, also the solution of my minimization problem necessarily will be invariant under this involution. So this means if I'm looking for xi minimizing the volume, then it will look as follows. So it will have the same first and second coordinate. So let me call it S. What about the third coordinate? Yeah, I mean, the third coordinate is fixed by the condition that we have log discrepancy equal to 1. And remember, this was our choice, or not our choice, this was our canonical weight here. So this tells us if the pairing with this vector has to be equal to 1, of course, then the last coordinate has to be equal to 1. Okay, so whatever the solution here is going to be, it has to look like this. And now it turns out that, or we can rephrase the volume which depends on xi. It now just depends on the choice of a real number, namely S, right? And this is always going to be a polynomial, in this case in S. And yeah, I mean, everything can be calculated here very explicitly. I mean, it's not hard to calculate the volume of such a truncated cone. And if you do this, you figure out this is actually a polynomial of degree 3 in S. But now we have an optimization problem. So we are taking the derivative of this polynomial. So we end up with a polynomial of degree 2. And yeah, I mean, we can just explicitly solve this polynomial. And what you get is, as solutions, you get 4 plus minus square root of 13 over 3. Okay, and yeah, of course, because we have we're looking for the roots of a polynomial of degree 2, we expect 2 solutions, and we get 2 solutions here. But remember that we only look for positive solutions. Positive in the sense that xi has to sit in the dual cone of our cone tor here. And as it turns out, only one of the 2 solutions actually sits in the dual cone. So this plus here is the solution we are actually interested in. So this is the positive solution. Okay, so what's remarkable here? I mean, the remarkable point is that this is actually an irrational number. So in particular, remember that originally we were looking for a Z grading, and then we observed a Z grading would correspond to a choice of a lattice point for xi. So we don't get a lattice point here, right? So if we plug in for S this irrational number, this is not going to give us a lattice point. The next idea could be maybe this is only a problem of rescaling. Maybe if we rescale it to the correct length, we can make it into a lattice point, right? So we are looking just for a lattice point on the ray generated by our choice of xi here. But now it turns out that actually there are no lattice points on this ray or on this line either. So the intersection with the lattice just consists of the origin. I mean, I don't count this one, right? So in other words, the line generated by psi is an irrational line in our vector space. So this thing here is irrational. So it doesn't really give us a grading, and it doesn't even give us a grading after rescaling. So the question is, what is the interpretation for this psi? I mean, we can see it like a generalization of a grading for our ring, but actually, as we will see in a minute, there's a geometric interpretation of such a psi. And so on the next board, I will talk about this geometric interpretation, and I will also talk a little bit about the relevance of this fact that we found here an irrational solution. I mean, already from a toric point of view, it's maybe a little bit surprising. Usually, if you work with toric varieties, you expect everything you see to be in the end rational and polyhedral. And here we get something which is not rational. Okay, but yeah, there's a relevance beyond this. Okay, so what's a geometric interpretation of the example we have just seen? Yeah, I mean, in order to move to geometry, we move to the spectrum of our ring R. So we get an affine variety, and we can assume we fix an embedding in some affine space for this variety. But it's not just a ring, it's a graded ring. So this means it comes with an action of an algebraic torus of dimension n. Let's call this torus maybe T. And what we can do is we can restrict this also to an action of the corresponding compact torus as 1 to the n. So let's call this H. Now, one interpretation for our choice of psi, I mean, in general, so if we choose a psi inside NR, then we can interpret this NR as being the Lie algebra of this compact torus. Okay, so this gives us some kind of geometric interpretation. Okay, now we go even further. So we want to assign a real manifold or a smooth manifold to this situation. And how do we get a smooth manifold? We take our singularity and we intersect it with the unit sphere in Cn. So we are looking for the unit sphere in Cn. So this will be a sphere of dimension 2n minus 1. And since in the beginning we assumed that X has an isolated singularity, so we are actually intersecting away from the singularity. So this is indeed a smooth manifold. And such an object is called the link of our singularity. So that's the link of X. And certainly the action of the algebraic torus is not preserved under this intersection. So, but what's preserved is the action of the compact torus. So we still have the compact torus acting here. And this is not hard to see, right? So multiplying a vector with an element of the compact torus does not change the length of the vector, meaning that in particular, if we started on the unit sphere, we end up on the unit sphere after multiplying with an element from the compact torus here. Okay, so And what does our choice psi give us on this smooth manifold? It's going to give us a vector field. Well, now we take a closer look at this smooth manifold, and we see actually it has more structure. It's not just a smooth manifold, it comes with an additional structure called a Zasakian structure. And I'm going to explain a little bit what this means. And what I'm eventually after are so-called Zasakian metrics. So I'm looking for a Zasakian metric G. So this is a Riemannian metric which is somehow compatible with our setting. And I'm giving some ideas what being compatible might mean here. And I'm not very precise, actually. So first of all, I want my vector field psi to be a unit vector field. So with respect to this metric, I want all the vectors to have length 1. Second property, I want psi to be orthogonal with respect to this metric to some hyperplane bundle inside the tangent bundle of our manifold. And what is this hyperplane bundle? So it's a hyperplane inside the tangent space. It's given as the hyperplane which is invariant under the complex structure. So this is a complex variety. So outside the singularity, we have a complex structure around, and we can just intersect TL with J applied to TL. So the tangent space inside the tangent space of X, the tangent space of L is not preserved under the complex structure, but there's a hyperplane which is, and I'm going to call this hyperplane D. And I want psi to be orthogonal to this hyperplane. Now a third condition is that I want my metric to be compatible with the complex structure. So if I take two vector fields, then I want that applying the complex structure to these vector fields leaves my metric invariant. Again, this doesn't make sense for arbitrary vector fields because I might get a vector field which is not even in the tangent space of my manifold. But it does make sense if I pick V and W inside this hyperplane bundle D. Okay, and there are actually more properties which I need to impose, but at the moment I can't remember them, can't recall them. So let's stick to these ones. Okay, so I'm looking for a Zasakian metric, and just repeating the pattern we have already seen 2 times, there are many choices for such a Zasakian metric, and I'm looking after a canonical choice. Okay. And before going into details about this canonical choice, let me talk a little bit about properties of such a Zasakian metric. And the first property I want to talk about is the volume. So I can ask for the volume of my manifold, of the link. And again, of course, what I'm talking about is the volume with respect to our choice of a metric. And as it turns out, this is actually closely connected to what we did before. It's exactly the volume of psi. Okay, so let me go back once and maybe explain a little bit. So we have chosen a psi, and then we are looking for a metric which is somehow compatible with this choice. So it has to fulfill certain conditions with respect to this psi. And now I can choose such a metric, and as it turns out, there are many choices for this metric, but the volume is actually, it stays constant as long as I fixed my psi. So it only depends on psi. So we learned something about the volume, the Zasakian volume of such a link. Okay, so a second property of such a Zasakian metric could be the Einstein condition. So this is usually just the property that the Ricci curvature of our metric G is equal up to a scaling constant in general, but we can assume that this scaling constant is 1 here, so that the Ricci curvature of the metric gives us back the metric. So this is called the Einstein condition. And one consequence of this is that actually such a metric is going to have constant scalar curvature. So yeah, remember that we have seen scalar curvature before in this talk. Okay, and another property of such a metric, or of our choices here, comes from the choice of psi. So remember, psi was a vector field, so I can follow the flow of our vector field psi. And yeah, a Zasakian metric is called irregular if it corresponds to a choice of a psi such that the orbit, or there is an orbit of the flow of psi which is not closed. So it doesn't close to an S1. And this just means that our choice of psi does not correspond to an S1 action on our manifold. So, and if you want to connect this with what we have done before, then this is exactly equivalent to the condition that psi spans an irrational line in the Lie algebra. So this happens if and only if R times psi is an irrational subspace. Okay, so let me revisit our example and maybe look. Before coming back to the example, let me talk a little bit about this Einstein condition here. And so the first question is, if you made a choice for a vector field psi, the question is, does there exist a Zasakian metric which fulfills this Einstein condition for our choice of psi? And there's a theorem by Martelli, Sparks, Yao, Futaki, Ono, and Wong, where the first three prove the first part, and the second three prove the second part. And what does this theorem tell us? It tells us that we can find a Sasaki-Einstein metric on our link if and only if our vector field, which is compatible with our choice of psi, then we must have this volume minimization condition. So the condition we were asked after previously. So we need to have the condition that the volume of psi is minimal in the sense, in the normalized sense, which we considered before. Okay, so this is just a necessary condition, but the second part of the theorem tells us that actually the converse is true, at least in the toric case. Okay. Now let's come back to our example and just sum up what we learned here. So we have seen for our example, we get such, or the solution of our minimization problem is such a choice of a irrational vector psi. So this means this, and yeah, this means what we get here is indeed an irregular Sasaki-Einstein metric on the link of our affine variety here. What was the affine variety? In this case, it was the affine cone over the de Pezzo surface of degree 6. And we had to intersect this with the unit sphere in the ambient affine space. And it turns out what you get here is S3 times S2 as just, I mean, the topological manifold you get here is S3 times S2. And at the time when this was discovered by Gauntlet, Martelli, Sparks, and Waldron, this was a very surprising result because it was conjectured before that irregular Sasaki-Einstein metrics do not exist. And they found even a toric example on this product of spheres. And actually, you can extend this example simply by increasing the Picard rank of our surface. You can find similar examples on connected sums of this guy. Okay. And so this actually happens, so you get higher connected sums of this guy if you increase the Picard rank of your surface. So we can ask what happens if you decrease the Picard rank of our surface. So we now just look at a cone over the simplex. And we can again try to make use of a symmetry, which we have here. I mean, we can just look at the 3 generators of our cone, and by permuting these 3 generators, we get an action on the ambient vector space, a linear action on the ambient vector space of this cone. And this just permutes all the coordinates of this vector space, right? And again, if we find everything is preserved under this action, and if we want to find a minimizer of the volume, then it has to be invariant under this symmetry. So this means psi has to look like, has to be a vector where all the 3 coordinates coincide. So it looks just like a multiple of the vector 1, 1, 1. Okay, and in particular, this of course is a rational subspace. So telling us that in this situation, we don't find an irregular Sasaki-Einstein metric. So at least every toric Sasaki-Einstein metric here has to be rational. It has to be regular. And so what we could further ask is, what happens if you not just looking for the toric case? So the point is, if you look what this this affine variety here gives us, I mean, this is just A3. And I mean, if you intersect A3 with a 3 times 2 times 3 minus 1 sphere, so you get just S5. So the link in this case is just S5. And you can ask, yeah, if we don't insist in having a toric situation, are we still able to find a regular Sasaki-Einstein matrix on S5? So this example just showed us at least we don't find any toric ones. Okay, and I mean, the theorem here is no, there are no irregular Sasaki-Einstein matrix on S5, even if you drop the condition of being toric. And I don't have time to go to the proof of this, but the idea is again to exploit a symmetry, very similar to this one, but the situation is going to be more complicated. Okay, so I have to skip this one. And the last thing I want to do is to talk a little bit how is the situation in the non-toric setting. So we have seen in the toric setting, actually the existence of a Sasaki-Einstein metric was equivalent to this minimization property of psi, for psi. And this doesn't hold in the toric case, in the non-toric case. So the question is, how does this generalize? And the key concept here is called k-stability. And let me first give the idea behind k-stability in terms of what we have seen before. Okay, so the first observation is that our choice of psi, which we in the meantime interpreted as a vector field, but there's also an algebraic way to interpret this, namely it also defines a valuation on our ring. Right, so the valuation corresponding to psi on an element of our ring, which is just a sum of homogeneous components, we can define this valuation as follows. We just take the minimum of all the pairings of psi with weights appearing in this sum. So we want Fu to be not equal to 0. And it turns out this indeed defines a valuation on our ring. And in the theorem of Martelli, Sparks, and Yao, they told us that in the toric setting, we get a Sasaki-Einstein metric if and only if our choice of psi was minimal among, or gave us minimal volume among all other choices of psi in this vector space. And now we have to refine this for the notion of k-stability. So we say L and psi, this pair is k semi-stable. Again, if the volume of psi is minimal, but not minimal among all possible choices of vectors in, so remember psi was just chosen out of NR, but minimal among all valuations. So now it is, the condition is much stronger. And this notion of k-stability turns out to be the correct generalization of the observation of Martelli, Sparks, and Yao, namely the theorem here by Collins and Sekaidi tells us that, again, we find a Sasaki-Einstein metric on our link, which is compatible with the vector field psi, if and only if this pair is k-stable. And here I'm cheating a little bit. I only told you what K semi-stability is. We have to strengthen this a little bit to get K stability. But I mean, somehow, yeah, morally, what holds here is once more that, remember, Sasaki-Einstein metric in particular meant that we have constant curvature. And what I tried to convince you is that K stability essentially means volume minimization. And similar to our very first example where we considered embeddings of the sphere into R3, we again observe that in this setting somehow both conditions turn out to be equivalent. So we can find a Sasaki-Einstein metric, which in particular implies constant curvature if and only if psi fulfills this volume minimization property. And here I'm going to stop, I think. Thank you for your attention.